Hello everyone, welcome. Let me tell you a story. About a month ago I had a splendid idea to invest in cruise stocks. And then everything changed. When the coronavirus struck. I don't know about you, but it seems quite logical that people don't want to travel as much when there's a worldwide epidemic on the loose. And you have probably seen the headlines that several cruise ships have been quarantined because of coronavirus outbreak. So, needless to say, my investment did not go so well. Anyways, what I wanted to do was try to predict when this epidemic or pandemic or whatever you call it will reach its end using the confirmed cases of the coronavirus that you can find on Wikipedia or anywhere. At the beginning of any epidemic, the disease or the spread of an infectious disease fits quite well with an exponential function, so we'll try to fit the confirmed cases of the coronavirus in mainland China to an exponential function and maybe gain some insights about that. And then I think that the exponential function would not be valid for very long, so we will also try to fit it to another function. So let's just get cracking, shall we? So here I have a Jupyter notebook open. First of all, we need some import NumPy. We're going to use stats models. The ordinary least squares, we're going to do a little trick to fit an exponential function using the ordinary least squares. And we also need to get a tool to add a constant. And we're going to plot it, of course, so we need matplotlib as well. There, that should do it. Oh dear lord, what's going on? It's fine, ignore that. So what we're going to do is we are going to create an array with all the confirmed cases from mainland China. You can find these on the Wikipedia page about the virus outbreak, or you could find them from the Chinese health department pages or whatever. I've already written them down, here they are. Actually, let's look at the Wikipedia page. Okay, so this is the official Wikipedia page of the Wuhan coronavirus outbreak. There's a lot of information here, a very thorough article, and here you see the actual data from the mainland China virus spread. You see the confirmed cases seem to be growing exponentially, but if you look at the actual growth, the growth has been slowing down for the past week plus. And these blue bars, they are the recovered cases, and the red ones are the dead people. God rest their soul. And there's also a country division by country, including this cruise ship, the Diamond Princess. So this is where I got the data from. These are the numbers that you see in the array here. All right, so what we're going to do with that. First, we're adding a constant. So our independent variable will be, well, just the days since the outbreak, equal to the length of the confirmed cases. And then we will add the constant to that, like so. And the add constant function, the only thing that does is add a column with only ones, so that our OLS model will recognize that as a constant term or intercept term. Alright, our model will be the OLS. And here comes my neat little trick. We will compute the logarithm of the confirmed cases, because the logarithm of an exponential function is a linear function, right? And we are going to first look at the, well, first we'll look at the first 2 weeks since the first confirmed case, like so. There we go. And we will need to fit the model, and immediately we could look at the summary page, which is stats models, the module we're using. It conducts a bunch of statistical analysis on the data, so this can be quite useful. And right now we don't have a lot of data, so a lot of the tests, they're not valid, but we are only interested in the goodness of the fit. And as we can see, the R squared is very high at 99.5%, meaning that 99% of the variance in the data can be explained by this simple model, right? So here we have a constant term, it has a coefficient, and we have a slope. Good. And now we will try to plot this to see how that looks. So we want to now compute the exponential of the predicted results. Thusly, of the x's for the first 2 weeks, and we'll label this as put this on several lines so it'll be visible. We'll label this as the fitted exponential function, and then I think that's how it's supposed to be, right? There you go. Yeah. We'll also include in the plot the actual data. So these are the confirmed cases of the coronavirus, and this will be a scatter plot, only dots, and we'll label this as the reported cases, China. We will also, we could add titles and so on, but I think it's fine, and we'll include a legend so we'll be able to see the labels, and then we'll show it, yeah? Oh. I only called it result. Alright, let's see, there we go. Okay, and as you can see, the fit is quite well. We have a few outliers here and here, but for the first 2 weeks of this epidemic, the pictorial evidence shows that, yeah, an exponential function is not too bad. But if we try to plot a few more of the observations, we will see that, or before we do that, let's just try to compute how long it would take for the entire population of the world to be infected with the novel coronavirus. All right, so the world population right now is around. I downloaded this number earlier from the World Population Clock. We have a lot of people, 7.76 billion, give or take a few. And days into the future, we'll start that variable at 0 and we'll increment it in some sort of loop, I think. And right now the number of infected is the last observation, right? So that will be number 14. So while our infected is less than the world population, we'll keep going, adding a day at each iteration, and then compute with our model, predict the number of infected people, which will be the exponential function of our result dot predict, and we need an intercept, which is 1. And then where do we start? At 13, and then add the days. And this will be an array, but we only want a number, so yeah, I think that should work. And then at the end, we will compute the number of days until all the world is infected is the days variable, right? And this is from after the first 2 weeks of the coronavirus. So this makes sense, right? We add an extra day to our model, how many sick, and then when we get high enough, the infected would be higher than the world population. I don't know if that makes sense, but let's see. So it takes 35 days if, as we assumed, the spread of the virus would continue going on at an exponential rate for the first 2 weeks, right? But this may not be the case. So let's look at what happens after the first 2 weeks, right? So we try to predict again. This time, just 2 days after the first couple of weeks, first fortnight, and we'll plot the real results as well. Same length. Let's show this. And as you can see, the model, the blue line here, is overshooting the number of infected people that has been observed so far. So it is not really good. In fact, let's try to include all the people in the model, and you'll see that hopefully that it won't be very good. So let's just do this. We have some confirmed people. There you go. We fit it, and we look at the result summary here. The model quite catches a lot, but you will see that it is very skewed, I think. So let's, yeah, there you go. This will be, this is not a very good regression, right? Because there are a lot of points that we don't hit at all with this fitted exponential function. So what we are going to do next is try to fit it instead to a logistic function. So a logistic function is sort of an S-curve. So we'll see that after a while, hopefully, that the number of infected people in China will start to plateau, right? Yeah, so let's just start a new section here, right? And we'll call this the logistic function fit, yeah. And then the logistic function looks a little bit like we have an X, and we also have some parameters in the model. There you go, see it? Yeah, so these are some parameters that will fit, and we'll use a very useful function from SciPy, the SciPy module, called curve fit. So we'll import that entire, well, let's just from SciPy.optimize import curve. Yeah, I think so. And we also import an accuracy metric from scikit-learn. Just the regular R squared, and yeah, right away let's just define the logistic function. It depends on X, A, B, C, and D, and it is a divided by it's disappearing behind my head there now. Okay, like so. 1 plus the exponential function of minus c times x minus d plus b. I think that should be it. Oh, metrics. Okay, what we'll do next is we need the confirmed cases, and we need to convert that to a NumPy array. Like so. And we also only need, if you look at our x's, which is just numbers from 1, 0, 1, 2, and so on, we still have that intercept column which we want to remove. So we'll do that. Say that x equals all the rows but only the second column. That should do it. And then we use the curve fit function. I think that it returns 2 things, so let's just check that first. Curve fit, what do you do? Yeah, x data and y data is fine. And it, yeah, returns an array with the optimal values, but also the estimated covariance. So we only need the first bit. So yeah. And we want to optimize the logistic function. And we want the x values are the x's and the y values are the confirmed. There you go. I'm hoping this works. And let's plot it right away. Yeah. So we'll plot the x's versus the confirmed cases. And these are the actual observations, right? So we'll label them the reported cases. And and now we want to predict with our fit. So let's make a variable confirmed pred for prediction. Logistic function x and our new parameters. So we'll plot that as well. X confirmed pred. We need a label. So this is the fitted logistic function. We'll add a legend and then show the plot. Hopefully it looks good. Oh yeah, look at that. Beautiful. Wow, wow, wow. You see, we have a very good fit here. And lastly, what we'll do is we will compute the R squared, or the explanatory value of this model, with the metric. Squared is the R2 score, and it takes in the actual values and compares them to the confirmed, or the predicted values. And we see that we have a 99.95 goodness of fit, which is very, very good. And as after a while, you can probably see it already from this this curve that it will flatten out and plateau. So lastly, what I want to do is figure out just about when is this going to happen. We are going to write some while loop with some expression. Let's say that, okay, more and more get infected, but the growth rate, or the number of people that get infected at each time this step, is decreasing. So after some point, only a few people will get infected. So it will asymptotically go towards some value, right? So I think what we need to do is rewrite two values for the confirmed cases at the current time point we're at, and the confirmed the confirmed cases from the previous time point, right? So we need, I'm going to call them confirmed now, for today, or yeah, latest prediction, which will be the last value to begin with, and the confirmed cases yesterday, or we just call it the confirmed then, that's in the past, which will be the second to last variable, right? And we'll do the same kind of thing as before. We'll increase the number of days from today. This is the cases from today, actually. So, and we'll also need we also need to know what day is it today, or the day since the outbreak, which will be our x's, the last value there. So while our confirmed now cases are, what we'll do is find the difference. So now we're assuming that they're always growing, which they will do in this model. So while this is larger than some arbitrary values, say 10, 10 people get sick every day is still bad, but it's not as many as now, where there are several hundreds or thousands. And for each of these iterations, we'll increase the day count by 1, of course, and we'll also update the confirmed then variable to equal the confirmed now, because now we're at the next step, right? And we will then compute our next prediction, which will take the place of the confirmed now variable. So that will be our logistic function now, which is the current day after the outbreak of the virus. We have that variable up there. We'll add the days from today into the future, and our parameters. And our parameters there are A, B, C, and D. Good. And after all this is gone, we'll say print in days, number of days of infected people will plateau at, and then the confirm now. Yeah, I think that should work. Let's try it. We have an error. Okay, so now the problem is that we're trying to compare an array with something else. So one of these variables up here, they are not an array, right? Oh, it's supposed to be then. Okay, let's try. Oh, whoa. Let's only include the integer value of this. Okay, here we go. So we see that in 23 days, the number of infected people will plateau. Oh, I don't know how to write French words, apparently. E-A-U, there you go. Plateau at 50,430, which is not too bad. Well, it is bad. So right now we have 37,198 confirmed cases. So if this prediction turns out to be true, that means that in about 3 weeks or so, we will see 13,000 more sick people, and then it will sort of stop, at least in mainland China. Let's try to plot it, just see that it has plateaued at that value. So we'll plot. So now we are going from 0 up to now plus days, right? And we want to use our logistic function. The same, yeah, and you know what? We're going to copy this and make a new x variable, like so. And then x, a, o, b, c, d. And indeed, hopefully the coronavirus epidemic is over by this point in time. Thank you very much for watching. I would like to thank you all for subscribing in the last few days, as it's been very fun. I have reached more than 300 subscribers, which I'm very grateful for. And I take that as an indication that I'm doing something right, so see you in the next one.
This is no Hollywood production. It is what residents of this ancient city have long feared would happen.
When the Fire Nation attacked,